Welcome, dynamic students. This mini lecture involves the concepts of impulse and momentum for particles or for bodies which are traveling translationally and can be considered to be particles located at their centers of mass. So for this, we're going to start out with our favorite Newton's second law, where we're going to restate that the force resultant, which is a vector, is equal to the time rate of change of momentum, and we're using the capital L to denote that this could be a body. Because it's linear momentum, we're not working with rotation, so this could be the center of mass of a body, any kind of body, rigid or non-rigid, or it could be a true particle. Either way, we're going to treat it like a particle. It's the center of mass. So we're going to integrate this expression and just express that result as in integral form. So we're going to integrate over time, over some interval of interest, integral over an interval. So we're going to integrate our force resultant, which could be a time-dependent function with respect to time from an initial to a final time. And we're going to call this integral, it's a definite integral, we're going to call it impulse. So it's force over time, force delivered over a period of time. When we integrate the other side, initially the other side was dl dt. We integrate that with respect to t, and we just get L at both of those times. So by doing a simple integral of Newton's second law, we find that we can define this quantity called impulse of force delivered over a time is going to be equal to the difference in final versus initial linear momentum. So it's a little bit of a twist on Newton's second law, but it gives us another way of looking at problems via momentum. Okay, and again, caveats as I scroll through my notes here. Remember that force, the F sub r, may not be constant with time. In a lot of cases it will be. Things like gravity aren't going to change with time. But in the case of maybe a spring that's compressing in a viscous fluid, it's going to take a while to compress, so that F equals kx won't be delivered instantaneously. There's a lot of scenarios in which your force resultant is a function of time. But if you know the function, all you have to do is integrate over the time of interest. The next thing to remember is that both L and F are vectors. So if a force impulse is only delivered, say, in the x direction, your momentum in the y is going to go unchanged. So these are separable by unit vectors in the orthogonal directions of whatever coordinate system you choose to use. So for instance, just as an example, here we have force resultant, the component in the x direction. Say we've taken that from our free body diagram. Maybe we have a function for it. We're going to integrate it from one time to the other, and we should be able to find our initial and final momentums, or the difference between those, as the result of the integral. Momentums linear and in the x direction. Now, of course, if we had something where the mass was constant, which we're going to assume for most of these problems, because linear momentum is equal to mass times velocity, we would also be able to deduce the change in velocity for a constant mass if we could integrate that force resultant over its time of application. So very, very useful, this concept of impulse being equal to a change in linear momentum in each vector direction. In many cases, we'll be backtracking using what we know about a system to calculate pre and post force interaction momentum and use that to infer the impulse that must have been delivered by that force, or decide what the maximum force can be given the time of interaction. There's a lot of different ways we can approach problems depending on what we need to know. Okay, so we've been talking about time so far, impulse and momentum all being time integrals. We can look at dividing up linear momentum of a body, remember we're talking capital L here, across all of its component parts. Remember that our momentum of a body is defined as the velocity of any little bit of mass of that body integrated over the whole body. Well, just like we did with the concept of center of mass, we can use a kind of a method of composite parts, we'll call it composite momentums here, to break that integral up into however many we need to. So if we have a cluster of particles, a system of particles, or bodies that can be considered particles located at their centers of mass, we can break up the linear momentum of the system into the sum of the linear momentums of the composite parts, just by using the properties of the integral of a sum as the sum of the integrals. And so we've written that out right here. So if we had a rigid body or a non-rigid body that we could break up into two parts, maybe it's going to explode and there'll be two parts flying off in different directions, we can consider the momentum of the system, maybe when it all has the same velocity, and then we can equate that to the momentum of part one, which may have a very different velocity than the momentum of part two. Nonetheless, they'll sum. And we can just calculate the momentum for as many different parts of that original body by just integrating the velocity of all of the parts in one part over that part by mass. And in a lot of cases, we'll just be looking at discrete individual parts, not subregions of a given body. So we can, if we skip to the end, we could just simply state this as the momentum of a total system is equal to the sum of the momentum of its component parts. So we can use that to advantage in the idea of collisions. So if we put, we're going to have to do a little scrolling here. Say the impulse is 0. We're not acting on a system with any forces. Then the difference in momentum from one time to the other is 0. It's conserved. It's not going to change. It's invariant. So if we had some kind of interaction of particles, like a collision, that didn't involve a force impulse, then we could say that the momentum of maybe a total system beforehand is going to be equal to the momentum of the system afterwards, which might involve one or more parts that weren't there before. So if we have something that's breaking up or colliding and combining in whole or in part, we can use the presence or absence of a force that would impart an impulse plus our integral of the sum is the sum of the integrals, equating the linear momentum of a whole system to the sum of the linear momentum of its parts to manage momentum in a collision. Did it change? Did it not change? If it changed, where was the force impulse? And add up the momentums in their orthogonal directions for all of the bodies. So those are the main concepts that we need to know about linear momentum conservation for particles or for bodies that we can treat as particles at their center of mass, and the impact, pun intended for later lecture. We're not considering impact yet. It's a special kind of collision that has an extra force energy component, but the influence of a force acting over a time on whether or not momentum will change from one time to another. Okay, having stated all of those concepts very briefly, let's use an example to kind of lock them in place. So this is probably a throwback to simple physics for a lot of you. So we've got a mass, a block sitting here on a surface. There's no mention of any friction, so we're not going to have any non-conservative forces. Gravity's acting downward on the block. And maybe this is at a ballistics reenactment police station where they're going to try to see what kind of gun fired a bullet. So someone's going to fire a bullet into this block and look at how it moves. This is used in crime investigations and definitely relies on these laws of physics. So the block has mass 1, the wood block, and the bullet has mass 2. These are really easy to measure. And we're going to assume that we know what the velocity is of the bullet hitting the mass and the angle that it's hitting it at. And those are, again, all things that are reasonably easy to measure, and easy to set up. This could be an experiment somebody does. And the bullet is going to embed in the wooden block, and the two are going to move off together to the right. And we want to know what is the relationship between the incoming bullet speed and the speed of the bullet embedded in the block combo mass that moves off to the right. So what's the relationship between little v of the bullet and big V of the bullet block mass? So to approach this, we can invoke our Our momentum of the system equals the sum of the momentum of the system components. So we can say L system is L bullet plus L block, which we can think of the L bullet plus L block as being the pre-collision state where you have a bullet with a momentum and a block with its own momentum, and that will be equal to the momentum, the linear momentum of the bullet embedded in the block combo. So basically bullet plus block and bullet block combo are both going to have the same linear momentum, which is the momentum of the system. So let's just use some simple trig to get the momentum of the bullet, remembering that momentum is mass times velocity, or velocity of the center of mass point. Bullet's pretty small, so we probably could treat the whole thing as a point at its center of mass. So the bullet's mass was mass 2, and so its velocity in the x direction is just its total velocity magnitude v times cosine theta, that angle that it's coming in at here. I hat, I've designated I hat x positive to the right and y positive going up. And its y component is negative mass, magnitude of the velocity sine theta in the j hat direction going down. The block was just sitting there at first. So in the initial condition, the linear momentum of the block is 0. It's got its mass, but it's got 0 velocity in the I hat direction. It's got 0 velocity in the j hat direction. Okay, the bullet block combo is given over here. It can't move up and down. It's not going to move up because basically there's nothing that would move it upward. There's no force impulse being delivered in the upward direction beyond the reaction forces, normal forces of the surface. So we know just based on the schematic that the bullet block combo is going to move horizontally, so it won't have a velocity in the j hat direction. So it's simply going to be the sum of the masses moving at whatever its velocity is, that's big V, in the I hat direction only. So that's L combo, which according to conservation of momentum is going to be equal to the sum of bullet momentum and block momentum, which is just simply the sum of the x components of each of these, which we're not getting anything from the block initially, so the bullet embedded in the block combo, its linear momentum is going to be simply equal in the I hat direction, is going to simply be equal to m2v cosine theta. So we can just do a little algebra and get this expression, which I think we were given a theta angle of something like 36 and a bit, which would give us a cosine theta of 0.8. So there's our ratio between, so our velocity that we're going to move off with our bullet block combo is going to depend on the ratio of the masses. So the mass of the bullet versus the mass of the total times the proportion of the proportion of the bullet's velocity that is actually pointed in the I hat direction. And so that's given by the cosine theta. So you can imagine this number would get bigger if the bullet were coming in straight horizontal, if we had more of its total velocity and therefore more of its total linear momentum being contributed in that I hat direction. So standard conservation of momentum. Something that we can notice, though, is that the linear momentum of the bullet block combo in the y was 0, in spite of the fact that if we applied conservation of momentum, we would have to have said, wait a minute, we can't ignore that j hat direction for the L combo, right? We're just kind of stating it 0 because, well, it looks like it didn't move. It's on the surface. It stayed on the surface. But in fact, there was something keeping it there. So now we can reach back to our idea of conservation of momentum, including a force impulse. So we had a j component right here of linear momentum in the form of the downward linear momentum of the bullet, which was part of the system. Now There's nothing down here. We've said that the L combo only has an X component. So by conservation of momentum, there had to have been a force impulse, because we can't go from a positive or negative, a non-zero linear momentum of the bullet block system. Who cares if it was only the bullet that contributed it? There had to have been some component of that linear momentum in the bullet block combo, or a force impulse had to act on the bullet block combo in order to counteract that. And that's exactly what happened. The normal force of the surface below the block exerted an upward force over some period of time as that bullet was embedding, to create a force impulse that basically negated this downward J component of linear momentum provided by the bullet, such that the bullet block combo didn't have a linear momentum in the J direction. So if you think about that, where the force impulse was being delivered by the surface. So if you think about this, if you were designing a surface that you're going to do this ballistic testing on night and day, now that you know that surface has to deliver a force over a given time, that might give you an idea of what you might want to choose for a modulus. How stiff, how durable, what kind of material you might want to use, so that you can keep doing this over and over again and the block indeed doesn't move downwards. Maybe you have to keep it dead still. So that might be a practical application of recognizing the fact that the force impulse that allows that block to stay at the same Y position has to be delivered by the surface, and you might need a material capable of doing it. So let's see if we can look at an expression for the force impulse in the normal direction. So if we had to get a material, we would have some idea of how to calculate it. So first off, we can assume the collision occurs over a period of time. It's not instantaneous. Nothing really is instantaneous. We assume things are, but collisions definitely aren't. So we'll assume the collision takes place over some time period. It's probably pretty short. But everyone has seen time-lapse pictures of bullets hitting ballistic gel and things like that, and moving through it and being able to see the response of the fluid. So if we can capture it on film, it's time dependent. So that means the normal force from the surface is time dependent. So it will be applied over a time period as the bullet embeds and becomes part of the block bullet combo. So we can get our arms around this with an FBD. Surprise, surprise. So here's our block with a bullet embedded in it right there. And at some point during the embedding process, kind of maybe at the end, we're going to have a downward weight force of the combination masses and gravity, and an upward force, normal force, counteracting that, if we are assuming that there's no acceleration in the J hat direction, which is what we're doing. So we can say, great, well then the force resultant must just simply be the normal force minus the weight of both of those components, and that'll of course be oriented in the J hat direction. So now we have a force resultant. We should be able to integrate that force over whatever duration that embedding process, that collision occurred. And in this case, the time-dependent force that we don't know is the normal force. The weight we're assuming here is constant. So normal force will be time-dependent via the n. The other force is constant. So we can just say, fine, we'll integrate it. Can find it somehow, but this will then have to be equal to the difference in the momentum from one point to another. So we've got the entire linear momentum expression here. So we got our combo, which only has a component in the I hat direction. We've got the bullet block, which only has a component in the J hat direction. Remember, the force resultant only has a component in the J hat direction. So we haven't really negated anything that we said about the I hat direction. It's fine on its own. Its pre and post linear momentum is exactly the same. No force impulse needed. No force impulse delivered. It's all in the J hat direction. So if we write this out looking only at components of the the linear momentum in the j-hat direction, we see that the post-collision linear momentum is 0 in the j-hat direction minus the pre-impact linear momentum in the j-hat direction, which was only in the form of the bullet. So we got minus negative m1 v sine theta. And I think this should have been m2 coming from the bullet. Yes, it should have been an m2 coming from the bullet. We'll correct that in the notes when they're posted. We'll just write a little 2 for now. Okay, get that a little corrected there, because there was no j-hat momentum of the block. There's no any linear momentum of the block to start with. So we can break our integral for our impulse up from the gravitational terms that we know. So we can say, all right, we have the weight effectively times the integral over the duration of the collision, which will just be a time. So it'll be weight times time, the duration of the collision, subtracting from whatever this normal force function is over time. So we can isolate the impulse from the normal force, which is this entire integral expression, equaling the weight times the total duration of the collision, plus, and this is going to m2, the pre-collision linear momentum in the j-hat direction contributed by the bullet. And we know from general characteristics of high-speed collisions that the total collision duration is really small. So this whole component tends to be pretty small. And so we can approximate the impulse needed from the normal force of the surface to be pretty much equal to the entire initial linear momentum of the bullet. So we can, if we know anything about the duration of the collision, we know at least what the total magnitude of that normal force will need to be, especially if we approximate it maybe as a constant as a first guess. It won't necessarily be constant, but we'll at least have our arms around it. So this is a good example of a case where we had a kind of a hidden impulse being delivered that in a lot of cases we would have ignored and just said, well, the combo has no linear momentum in the y because it keeps going straight. Well, it's going straight and has no linear momentum in the y direction because a force impulse counteracted what we had going in. So that is that. We will do another rectilinear impulse momentum example, and then we'll move over to impact and fluids for other mini lectures dealing with impact and momentum, but we'll do one more simple collision. And this one basically looks at the corners of the box of types of collisions you can have. Most collisions will be some blend of these two. So we've got a couple of masses. They're sitting on the floor and they have their equal mass. We're going to consider them particles if their centers of mass. One's stationary, the one that's kind of crosshatched is stationary. And there's another one moving towards it in the positive I-hat direction with a velocity v. It's all in the I-hat. And we want to know what the post-collision velocities of both of those masses are under two conditions. One, the blocks stick together. Second, there is no system loss of kinetic energy. So no system loss of kinetic energy. So we'll find out more what that means as we look at impacts, higher speed collisions. But things where you have no loss of kinetic energy tend to be elastic collisions. We're not losing any energy in the system due to friction. So let's look at scenario one, which is going to be very close to the bullet block. And this is really a simplification of that. So we can say our initial system momentum is just mv in the I-hat direction. It's not 2m because the other m doesn't have any velocity. The final system linear momentum is 2m times whatever the final velocity is. Simply solve for v final. Masses cancel out and it's half. So basically you've conserved linear momentum, you double the mass, you have the velocity. So pretty easy. And we could say this and make it very simple because we knew that they moved off as a combo mass, a single unit with the same mass. Okay. If we say kinetic energy is conserved, we can't make any assumptions on whether anything sticks together or doesn't. So let's assume it doesn't stick together, and then if it turns out the velocities are exactly the same, we can infer that they must have been traveling together. So, well, again, we can still invoke conservation of momentum. Linear momentum of the system initial equals linear momentum of the system final. And we're also going to invoke kinetic energy. Initial and final was the same. So we're going to say MV1 is going to, M1 V1 equals M2 V2 in this case, since we're working in 1D and with particles, and we can say 1/2 M1 squared equals 1/2 M2 V2 squared. Up here, by the way, if we went back through and looked at kinetic energy, we would find that it wasn't the same. We can even kind of do a little head check here and say initial kinetic energy was 1/2 mv squared, no v coming from the second mass. If we insert a v over 2 into kinetic energy, we would get 1/2 2m, which is just m, and then we would have v over 2 squared. So we would be squaring that 1/2, and then we'd end up getting a factor of 2 in the denominator. So we have actually a kinetic energy reduction. It was not conserved in the first case. Well, in the second case, we're gonna make it be the same, and then we're gonna see what the impact is on VF. All right. So system linear momentum initial, MV final, M, and some V1 and some V2. So here's our conservation of momentum expression. Kinetic energy. Kinetic energy is initial 1/2 m magnitude of the velocity squared, and final V2, just written this as the velocity for either mass. So final one was stationary, so in this case, we're assigning the velocity of either 1 or 2. It's v. So we know v initial, we don't know v1, v2 final. So we know the final kinetic energy 1/2 m v1 squared plus 1/2 m v2 squared is going to have to equal the initial. So here's our conservation of kinetic energy. Okay, so if we drop the 1/2s and the masses, we can simplify our kinetic energy conservation expression to be our initial velocity of that first mass squared equals the sum of the squares of whatever the velocities are of the other two. And from momentum conservation, we've got the velocity of that initial mass is equal to the sum of the unsquared velocities of block 1 and block 2. So we have two equations and two unknowns, v1 and v2. So if we solve them together, with the squared terms, we end up, of course, having two different sets of answers. So we can either have, as it turns out, v1 being 0, this is post velocity, and v2 having the same velocity as the initial mass, or mathematically, we can have the first mass retaining its velocity and the second mass sitting still. Now this one's physically impossible because to do that, the first mass would have to travel through the second mass to stay on course moving forward. So this is a mathematically plausible but physically impossible scenario. So what we get is the first mass stops and the second mass continues on with the exact same velocity as the first. So this is like some of those little desk toys where a little ball comes in and hits a stack of balls and the ball on the other side flies out. This is the conservation of kinetic energy and momentum, the scenario that we're looking at here. So real collisions are going to be somewhere between the two. Obviously, our bullet embedded in the block was very akin to our first scenario where you have something stuck together and continuing. Sometimes you'll have things rebounding partially. You'll have some loss of energy, large or small. And when we start thinking about how much energy do we have lost during the interaction of a collision, where things are elastic or plastic, are they going to smoosh together and or are they going to spring apart? We're starting to think in terms of the next topic, impact, where we're looking at actual deformation of particle bodies during a collision event, and then their rebound. So we'll start invoking concepts that you'll see again in mechanics of materials of elastic and plastic strain. So we're really going to let those bodies deform in our study of impact, and then look at what happens as a result of that, the nature of that deformation, on how our impulses and conservation of momentum add up. So that's another topic in our impulse and momentum of particles. But this concludes our basic discussion, conservation of momentum and impulse. So linear momentum of a system before and after any kind of collision event is going to be the same unless that system is acted on at any time by a force over a time, therefore given an impulse. And the linear momentum of a system is equal to the sum of the linear momentum of its composite parts, both before and after any kind of collision event. So that's the takeaway.